Patricio. Thank you very much for your presentation. Now, I have a big pressure. Excellent presentation for me. Thank you very much, Patricio, for this invitation and this opportunity. It is a pleasure and honor for me to be part of this course, okay? My name is Andres Pastor. I am materials engineer and welding inspector and teacher in the welding technology in Institute Sabato too, and which depend of the University of San Martin. And I also teacher and instructor of welding metallurgy and welding process according standard in the National Institute of Steam Making. And I am a member of the Argentinian International Working Group of ESME, okay? Thank you very much for everyone. I will start with the presentation, okay? This is a brief summary of this class. Firstly, we want to talk about the general requirement of standards, and then I will try to explain the scheme for the welding procedure qualification according to ESME section 9. And then I'm going to give you a definition of welding variables. In this point, we will try to understand what are the objectives of variables according to ESME section 9. Finally, we will work in quick examples and case study before the conclusions, okay? Please, during the class, you can write the question in the chat with your email address. It's possible, Patricio. Today, we have a short time, but if I can answer the question today, I will send you my comments by email, okay? Okay, so I think that we can begin this class with the following questions. What do we need to know about welding to manufacture a welded component, okay? I would like to give you my personal experience about the answer of this question, okay? When I was younger, when I was 24 years old, I started to work in the National Commission of Atomic Energy in Argentina. And during my academic training, I learned about art physics, heat transfer, and welding processes, and welding metallurgy, perhaps the same knowledge that you will have at the end of this course. However, my first work was the material selection for internal components in nuclear reactors and the definition of the welding procedure qualification requirement for these components. It was a really interesting and challenging work for me. However, I remember the words of my boss who said me, Andres, your objective in this group is understand this book. And remember that he gave me the ESME section 3, subsection NG, that are the rules for construction of core support structures, okay, in nuclear reactors. And I was working perhaps during 2 years without martensites, without peak temperatures, without cooling rates, without globular transfer, only working with code and standards, okay? And so, what I learned about this experience? I think that the knowledge about welding is very important and fundamental because it allows us to understand the variable that affects the mechanical properties, the chemical properties, the phase transformation, residual stresses, among other things, okay? This is the most beautiful part of the weld, okay? For example, in my case, I love studied about welding metallurgy, okay? However, nowadays, it's not possible to consider an engineering project without using standard and codes because they are based not only in investigation data, but also in service experience. And this is a very important in our engineering project, okay? The service experience of material, the service experience of the design criteria, the service experience of the welding processes, okay? So, I will continue. Before talking about the welding standard, it is important to establish the main objectives of the standard in general, okay? The standards have 4 objectives, which are specify, simplify, unify, and the balance, okay? Specify means define precisely some characteristic or set of characteristics. For example, the specification of the base metal for a welding process, and simplifies mean reduce the number of features to necessary amount. For example, the dimension of filler metals. Unify, in other hand, means establish a common criteria, for example, to test required in welding procedure qualification. And the balance refers to make a balance between the demand of the user and capability of the manufacturers. Okay, these four objectives define the purpose of the standards, all standards in the world. I think that the standardization is an essential tool in this world, okay, particularly in this world today, where the materials, equipment, personnel, and operators in generating data is come from different parts of the world. Here in this slide, I want to show you a very interesting example of the need to standardization. This is an old article that I found in a newspaper, and this news is about an orbiter called the Mars Climate. In this mission, the operator detecting an erroneous trajectory which caused the destruction of the orbiter. What was the problem with the mission? The mission was unsuccessful due to the failure to translate the English unit to metric units. Okay, this is an official report of NASA. This is a very simple mistake with enormous and expensive consequence. Very easy to avoid with a good work of standardization. This is a very simple example, but I think that it's very important to know what is the objective of the standardization. Okay, so you had a class about different standards, about the Canadian standard. It was excellent, a very interesting class. So you know that exists a huge amount of standard around the world, and it is impossible in a class to be able to explain completely the scope of one standard at least. But I want to show you just some example to get important concept about the welding standard. Today we will work with ESME code. Particularly, we're going to use the ESME BPV code, which means the boilers and pressure vessel code. Okay, and in this class we will work with the ESME BPV code section 9 that includes the requirement to procedure and performance qualification in welding, brazing, and fusing. Okay, using this standard, we want to answer different questions. Firstly, what is a welding procedure specification, or WPS? In second place, how is a welding procedure specification developed? And finally, how is a welding procedure specification qualified? Okay, so the first question is, what is a welding procedure specification, or WPS? To have a precise definition, we have to go to ESME section 9 in the paragraph QW 200.1. And these paragraphs say a WPS is a qualified welding procedure prepared to provide direction for making production weld according to the code requirements. The WPS provide direction to the welders or welding operator to assure compliance with the code requirement. This is the definition of ESME section 9. And this definition has three important concepts. Firstly, a WPS provide direction for making production welds. Okay, this sentence indicates that the WPS shall be a tool for the execution of welding works. It is very common, unless in Argentina. I don't know if the same case in Canada, but in Argentina, it's very common to see that the WPS are in a quality control office of the companies. I think that this WPS is useless. I don't trust these companies. The WPS need to be in the welder's hand. This is the appropriate place to WPS, a welding procedure specification. And this definition, in this definition in second place, we can read that the WPS assure compliance with the code requirements. And this is very important because the objective of qualifying a welding procedure is assurance compliance with the minimum requirement defined by the code, typically the soundness and the mechanical requirement, okay? And finally, a WOPS has to be qualified. The purpose of the welding procedure qualification is to provide evidence that the proposed welding process is capable of making production joints that meet the mechanical requirement defined by the construction code, okay? To carry out this demonstration, it is necessary to make a test coupon that shall be subjected to the test and examination to demonstrate compliance with the minimum mechanical requirement. So these are fundamental concepts about the WPS. First, provide direction for making production welds. Second, assure compliance with the code requirement. And the last one is qualification. So it's very important in this definition to know that each WPS defines the condition under which the welding process shall be performed. These conditions are defined as variables. This is the name that assigns the code to this condition, variables, according to the section 9. So, okay, the next question that we had is what is a procedure record or PQR, okay? And the paragraph QW 200.2 gives a definition of PQRs, okay? In this paragraph, we can see that the PQR is a document where the variables during the welding of the test coupon are recorded, okay? And moreover, the PQR also contains the test results of the specimen extracted from the test coupon. This is that information that shall be included in the PQR, the variables during the welding of test coupons and the test results, okay? Here we have to take into account the following. Recorded variables in PQR normally fall within a small range or unique value. Okay, for example, the base metal thickness is a unique value, and on the other hand, the heat input has a small range due to the normal variation of the welding parameters, such as the current, the voltage, or welding speed. The variables used to welding the test coupon are called actual variables, okay? Actual variables are the variables used in the welding of the test coupon. And these variables are very important because they are the base to define a bigger range of variables in the WPS, okay? I will give you an example about this concept. For example, let's suppose that we are making a welding procedure qualification where the base metal is a carbon steel seamless pipe. For example, this material specification in the screen. For example, in this case, is an A106 grade A, okay? So this variable is an actual variable, okay? This is the material of the test coupon. This actual variable regarding to the base metal qualify a big amount of other materials, for example, welded and seamless carbon steel pipe, carbon steel forging, carbon steel plates, sheet and strip, carbon steel bars and shape, among other materials. These materials are qualified variables and they shall be included in the WPS. Okay, this is a very important concept. Each actual variables qualify a more extensive range of variables, call it the qualified variables, which are included in the WPS. So here we have a flow chart where we can see the different steps to qualify a welding procedure. Okay, I think that it's important prepared preliminary WPS, which isn't a qualified WPS. It has the only purpose to be a guide during the welding of the test coupon. And with this preliminary WPS, we had to weld in the test coupon. During this step, we had to record the actual variables of the welding in this instant, in this step, the second step. Okay, and at this point, it's important to know that ESME section 9 defines the variable that shall be recorded. Okay, when the test coupon was finished, we had to follow with the test for the welding procedure qualification. In this case, of rejected tests, the qualification is disapproved. Okay, so it is necessary a new welding test coupon. And in case of approved test, you can pass to the third step, the PQR. Okay, here you have the third step, the PQR, in case of approved test. In this step, you have to include the actual variables recorded during the welding of test coupon and the result of approved coupon test. Okay. The last step is the writing of qualified WPS, and this WPS shall be developed with the qualified range variable defined by the section 9 according to the recorded actual values. Okay, this is the process to qualify a welding procedure. We previously talked about the variables. Okay, we say that the parameters and characteristics of the welding process are defined as variables. And in this slide, we have the 4 types of variables defined by the ESME section 9. We have the essential variables, and that are the variables that strongly affects the mechanical resistance and ductility. We have the non-essential variables. They are the variables that don't affect the mechanical resistance or ductility. The supplementary essential variables, they are the variables that strongly affect the toughness of the welded joint. And finally, the special process variable, that are the variables that affect the mechanical or chemical properties in special processes. Well, so one of the objectives of this presentation is understand which variables shall be included in all WPS. Okay. Paragraph QW 200.1 is fundamental because it defines the variable that shall be included in all WPS. This paragraph says 3 important things. Here you have in the presentation this paragraph QW 200.1, and this paragraph says 3 important things. Firstly, all WPS shall contain essential and non-essential variables. Okay, this is a mandatory requirement. In second place, the supplementary essential variables are included only when required. Okay, when the ESME section 9 say when required, it is referring to the construction code. Okay, the supplementary essential variables are activity when it's necessary to demonstrate the toughness of the welds. Obviously, it's not always necessary because it depends on the service condition, and depends on type of material, depends on the geometric condition, for example, the thickness, among other factors. So the construction code defines when the toughness tests are required in the welding procedure qualification. Okay. So, the finally important concept in this paragraph is that the QW 200.1 say that these variables, essential, non-essential, and supplementary essential variables, are listed for each process in QW 250. Okay, this is an important point into the ESME section 9. So, a good starting point to use section 9 are tables QW 250, because these tables define the different variables for each welding process. Okay, so here we have an example of one of these tables. In this slide, you can see the table QW 253 applied to the stick process or shielded metal arc welding. Okay, and in this class, we will work only with this table. But you have to remember that there is a table for each welding process. Okay, each welding process has a table QW 250. Well, and this table is divided into different groups of variables. We have here the joint variables. Okay, the QW 402. We have the base metal variables. Okay, and the filler metal variables. You have to remember that this table is bigger. Okay, this is a little part of this table. Each group of variables include specific variables and define if this is an essential, non-essential, a supplementary essential variable. So here you can see that this X indicates what kind of variable is, for example, the capital T qualified. In this case, capital T qualified is an essential variable, okay? So, in this slide, we have an example to use this table. I think that the best way to learn how to use this table. For example, let's analyze the variables associated with the base method. Here you can see, for example, that this variable have 3 essential variables and 2 supplementary essential variables, okay? And in the ESME section 9, for example, capital T is the thickness of the base metal. Okay, you can see the capital T in this row, and in this row is the thickness of the base metal. For example, during the welding procedure qualification, I had to define what is the base metal thickness qualified according to the test coupon thickness. To this definition, this table have a variable called capital T qualified. Okay, so sorry. Okay, the question is now, how can I define the qualified range for base metal thickness? Okay, go to the table, and for example, the QW 403 is the paragraph applied to the base metals. Okay, and the paragraph 0.8, for example, in this variable, in T qualified, the paragraph 0.8 is applied to this specific variable. So the description of the qualified range of this variable is in the paragraph QW 403.8. Okay, in this point, we have the description, in this paragraph, we have the description of this variable. So I would like to say that this is a good starting point to study the ESME section 9. This methodology to analyze the variable is equal for all variables. In this sense, the ESME section 9 is a mechanical code. If you understand the process with one variables, you can advance with the other variables with the same analysis. Okay, this is a good advantage that have this code. So now we are going to talk about some specific variables defined in ESME section 9. And one of the most important concepts generated by this section is the definition of P numbers. Okay, the P number is a grouping to base metal based on chemical composition, weldability, and mechanical properties. The purpose of the P numbers grouping is to reduce the number of welding procedure qualifications that are required to carry out a project. In general, we can say that if I qualify a welding procedure with a specific material into a P number group, this welding procedure is qualified to welding all materials into this P number, okay? I will repeat this concept because it's very important. If I qualify a welding procedure with a specific material into a P number group, this welding procedure is qualified to welding all materials into this P number. Okay, there are exceptions to this rule, but this is the general concept about the P number. So here we have a table with the different P number and the typical chemical composition for each one. P number 1 are the most common material because that includes the carbon manganese, and carbon and manganese silicon steels. You can see this is the P number 1. So then we have different low alloy steel, typically chromium molybdenum steel. And after the P number 5, we have other families of materials such as different types of stainless steel, ferritic, martensitic, austenitic, stainless steel, etc. Non-ferrous based materials, for example, the aluminum, the copper, nickel, etc. Here you can see in the last numbers for example, that the P number 41 to 49 are the nickel and nickel-based alloys. Okay, so let's start working with this variable. Okay, let's start working together. Here we have a little part of the table QW422, which is included in section 9. This table is very important because here we find the assignment of P number to different specification, type, grades, and materials. Okay, and in this table, excuse me, just a second. Okay, here. And in this table, the first column, this column, define the material specification. Okay, the material specification of the base metals. And in the second column, we have the designation, type, or grade of our materials. Okay, and in this column, the fifth column, we have the assignment to the P number. Okay, just excuse me. Okay, okay, here. Okay, we want to study this table with some example. It is very easy to use. Okay, in the first row, we have the material specification A36. This is a typical base material to structural use. Here you can see, for example, the nominal composition, and typically are plates, bar, and shapes. And here you can see that it is a P number 1. Okay. Then we have, for example, other material specification. In this case, the A106 grade V that is applied to seamless pipe. And in this case, you can see the nominal composition and the P number is 1, 2. Okay. So finally, we have other material, in this case, forging. According to this material specification with this grade, and however, the P number is P number 4 because the chemical composition is different. Okay, in this case, is steel and chromium molybdenum and silicon steel. Okay, so this table is very easy to use. Okay, so let's continue and analyze the P number variable. The table QW250 is the starting point to define the qualifier range. And in this case, we can see that we have a variable called P number qualified. Okay, this variable. Remember that this variable is applied to a stick process. Okay, you have other table for other process. And it is an essential variable. Okay, this is an essential variable. And this means that if I modify this variable beyond the qualifier range, I have to make a new qualification, a new procedure qualification. So this is the paragraph, in this case, the QW 403.11, okay? And this paragraph says that the material included in the WPS shall be qualified by a test coupon that was made using the base metal defined in QW 424, okay? Here we have a new reference, so we go to analyze this paragraph, okay? And the paragraph QW 422 includes a table that defines the qualified material range based on the material used in the welding procedure qualification. Okay. In this slide, you can see the part of this tile. This table is bigger too. Okay. And in the first column of this table, we have the base metal or metals. Okay, used in the test coupon. Okay. So here we have the actual variables. The first column indicates the material included in the PQR. Okay. So in the second column, the second column shows the qualified range according to the base metal used in the test coupon. So the second column defines the range that we have to include in the WPS. Okay? So you can see that the first and second row in the first column define the general condition of material in the test scope. The first row is the case where the welding is done between materials in the same P number, for example. Excuse me. Here. The first row, say one metal from a P number to any metal from the same P number. Okay? Here we have one of the most typical cases in the welding procedure qualification. And the second row is applied to the welding between two materials included in different P number. From third row to ahead, there are specific cases applied to particular P numbers. Okay, for example, in this row, you can see that this condition is applied specifically to P number 4. Okay, I will give you an example to use this table. Okay, this is a quick example. We will consider a test coupon of austenitic stainless steel, for example, a plate of this material specification. Okay, so the first step is define what is the P number applied to these materials. Okay, to the objective, I have to go to the table QW 422, and here we have this material specification. Okay, this is a P number A. Okay, this material is a P number A. So now I defined the P number. Okay, if you analyze this complete table, you will see that it hasn't a specific row applied to the P number A. So we have to use the first row. Okay, this is a P number A according to the table QW 422. So I had to apply the first row, and the first row define this qualified range of base metal. Any metal assigned that's P number. This means that all P number A base metal are qualified. Okay, in this case. Go to second quick example. In this case, the test coupon is a low alloy steel. For example, a pipe, seamless pipe, according to this material specification. So I have to define the P number. Here we have the material specification, and this is a P number 4. So this is a P number 4 according to the table QW 422. And if you go to the table QW 424, we can see that we have a specific row to this P number. Okay, here you can see that the welding P number 4 not only qualify P number 4 to P number 4, but also combination the P number 4 to P number 3 and P number 4 to P number 1. This is the qualified range of base metal. All P number 4 are qualified, plus combination P number 4 to P number 3 and P number 4 to P number 1. Okay? You have to remember that the first column is the actual variables. Okay? For example, the material specification of the test coupon. And the second column is the qualified range. Okay? That shall be included in the WPS. So this is a brief summary of the necessary step to define a qualified base metal range. In the first step, we had to define the material specification. Okay? In the second step, we had to go to the table QW 422 to define the P number. And then I had to go to the table QW 424 to define the range of qualified base metals. Okay? This is very important that one material specification define a bigger range of base metals. Okay? So here we have another example. In this case, I would like to go to the blackboard to resolve this exercise. This example is very easy. You have to consider a test coupon that was welded using two base metals. Okay, this material specification welded to this material specification, and we have to complete the yellow boxes of these PQRs. Okay, this is very easy. I changed the camera to go to the blackboard. Just a second. I don't know if you can say the blackboard okay.
Yeah, it's visible.
Yes? Okay, perfect. So, in this problem, we have to complete the PQR, okay? Remember the PQR contain the actual variables. Yes? So, in this case, I have a test coupon with these materials. Yes? This is the material that defined in this problem. So, on the other hand, the other side we have this material. Okay? This is my test coupon. So, I have to define the difference. I have to complete the yellow boxes in this PQR. So, I have to define in first place the P number of these materials. Okay? To define this P number, I have to go to the table. Remember, the first step is go to the table QW 422. Okay? So, I don't know if you have this table, but I will give you the result. This is a P number 1, and this is a P number 3. Okay? So, I have to complete the PQR. In the first boxes, I have to include the specification. Okay? In this case, the specification are these. Okay? So I have to include this specification in the yellow boxes. Okay? Then I have to complete the grade of materials in the second boxes. Okay? In this case, the grade materials are grade 70, and this is the grade of the other material. Okay? So I have to complete grade 2 plus 1 and grade 70. Okay, and the last step is to complete the P numbers. Okay, in this case, I have to include the P number that obtained in the table QW 422. This is a P number 3 to a P number 1. Okay, so this is a very easy example, but it's important because this is the first step when we make a welding procedure qualification. Is define the actual variables in the PQR, because this variable define the qualified range. Well, I think that we have, so sorry. Okay. So here we have the result. So this is the last exercise of this section. Can you see the screen? No, so sorry. Okay. So the next exercise. In the next exercise, we have an approved PQR was carried out using these materials. This is a typical chromium, molybdenum, CNS pipe. Okay. So, in this case, the question is, it is possible to use this PQR, okay, to generate a WPS for welding different materials. And we have two different combinations. In the first case, we have the welding of these materials. Okay, this is a plate, typically in the manufacture of pressure vessels. And in the other part of the question, we have this combination of materials. One, two. Okay. So in this exercise, we have to pass for the different steps that I defined previously. Okay. The first step is define the P number. Okay. To define the P number, I have to go to table QW 422. Okay, and then I have to go to table QW 424. Okay, so then I have to compare the qualified range with these conditions. Okay, so in this case, this material is a P number. I don't know if you have the table QW 422, but this is a P number 5A. Okay, so the qualified range of this P number is P number 5A to P number 5A plus P number 4 plus P number 3 plus P number 1. Okay? This combination, P number 5A to P number 5A, P number 5A to P number 4, P number 5A to P number 3, P number 5A to P number 1. Okay? So, if possible, well, this material with this base metal, with the PQR with this base metal, okay, I have to define the P number of these materials. Okay, go to the table QW 422, and in this table, going to see that this material is P number 1. Okay, so is possible, well, a P number 1 to itself, according to this range, is not possible. Okay, so I can weld this material with the PQR proposed. Okay, go to the second option. In this option, I have to define the P numbers. Okay, go to the table QW 422, and this material is a P number 5A, and this materials is a P number 1. Okay, so this combination is included in the qualified range. Okay, P number 5 to P number 1. So this means that it's possible to weld this combination using a PQR, which actual variable of the base metal is this material specification. Okay. This is a quick example to use this concept of P number. It's very easy, but you can go deep in this concept because it's very interesting, the concept of P number. Okay. So, okay. Okay. Now we're going to talk about the base metal thickness and how define the qualified range of these variables. Okay. If we go to table QW 253, we can see that the variable capital T qualified is reference. Okay. And it is an essential variable in the welding procedure qualification. Okay. You can see the table, and the capital T qualified, remember the capital T qualified, the capital T is the base metal thickness, okay? And this variable is an essential variable. So, here we have their paragraph, okay? In this case, to this specific variable, we have the QW 403.8, and here we have the paragraph, okay? So we can see the paragraph QW 403.8 is referenced. If you go to this paragraph, you are referring to paragraph QW 451, okay? So this paragraph is very important because it includes different tables where we can define the qualified base metal thickness, okay? So here we have the table QW 451.1. So sorry, but I have a problem with the numbers in English. And in this table, we have a lot of information about qualified base metal thickness, about qualified deposit weld metal thickness, and necessary tests for the welding procedure qualification. However, we will focus on the qualified thickness of the base metal, okay? So in the first column, you have the thickness of the test coupon, okay? This is our actual variable in the welding procedure qualification. And in the second column, we have the range of qualified capital T of the base metal, okay? So, and so in the last column, we have the type and number of tests required. For example, the tension test, the bend test, the different tests that are necessary to the welding procedure qualification. So we will work only with the base metal thickness, okay? This table is very easy to use. In the first column, we have the thickness of the test coupon, and the second column is dividing the minimum and maximum qualified thickness according to the test coupon thickness. So the qualified range is defined by the minimum and the maximum qualified thickness. It's very easy to use this table, okay? So here we have an example. Let's suppose that we have a test coupon of 15 millimeters in thickness, okay? So, this thickness is into this row, okay? Here we have in this row. Remember that the first column is the test coupon thickness, okay? So the minimum qualified thickness is 5 millimeters, okay? You can see it. Excuse me, I'm going to take a pencil here, okay? 5 millimeters, and the maximum qualified thickness is 2 times capital T. In this case, capital T is 15 millimeters, okay? So the qualified range in this case is from 5 millimeters to 30 millimeters, okay? Very easy. So here we have the last, we have another quick exercise. and where we had to approve it PQR, carry out with base metal with the following thickness. We have 19 millimeters and 38 millimeters. So we have to determine which PQR can be used to make a WPS for production wells with base metal thickness of 90 millimeters to 150 millimeters. Okay. In this case, we have to define what is the qualified range of the base metal thickness. For example, in the case of 19 millimeters, the base metal thickness is from 5 to 38 millimeters. Okay. The case of is 5 to millimeters. So in the other case, we have this range, this qualified range. Okay, we are in this row where the qualified range is from 5 millimeters to 200 millimeters. So according to this problem, okay, only the second PQR can be used for this range of thickness. Okay, I know that I am going too quickly because we have short time, but if you have any question, you can write me in the chat. Okay. Okay, perfect. So give me just a second. I don't know if it, so. I will write the qualified range in this slide. So sorry, just a second. I have a problem with the pencil. Here we are. Okay. The first PQR, this PQR, according to the table QW 451.1, has a qualified range of from 5 millimeters to 38 millimeters. Okay, and the second PQR has this qualified range. Okay, from 5 millimeters to 200 millimeters. So the question is, what? So here, okay. So in this problem, we had to determine which PQR can be used to make a WPS for production well between base metal thickness of 17 millimeters to 150 millimeters. This qualified range, the first PQR, for example, doesn't cover this range of base metal thickness. Okay. However, the second PQR covered this range of base metal thickness. So the answer is the second PQR. So the second PQR can be used. So okay, and this is the last variable that we want to analyze in this class. And this variable is applied to the filler's metal. Particularly, we want to describe the variable called F number. Okay, the F number is a grouping of filler metal very similar to P numbers because it has the same objective, that is to reduce the number of procedure qualification. before the F number grouping appears, each combination of filler metal require a separate welding qualification, the same as with the base metal. And this requirement generated a huge number of welding procedure qualification. And in this sense, the F number is very similar to P number grouping. However, the main difference is the grouping criteria. In this case, in the case of filler metals, the group are based on the operating characteristic of the filler metal. It doesn't mean that the chemical composition is not important. Actually, there is other variable applied to the filler metal which consider the chemical composition, call it A number. But this is another story. This is another variable, okay? What are the operative characteristics of the filler metals? Okay, well, this is a good question. And in case of a stick electrode, the operative characteristics are defined by the type of covering, for example, and it's different the operative characteristic if you have a high cellulose covering, high titanium or rutile covering, or low hydrogen covering. Okay, are different the operative characteristic. The operative characteristic is related, for example, to the welding position, to the type of current, etc. Okay, this is the criteria of this grouping. Okay, the operative characteristic is very different to the P number, which the grouping criteria is the weldability, the chemical composition, and mechanical property. This is very different. So let's start from the table QW 453. If we go to this table, we can see that the F number is referenced, and it is an essential variable in the welding procedure qualification. So it is a variable that affects the mechanical properties according to this definition. So here we have the F number. The reference, the paragraph that is applied is the QW 404.4. Okay, here we have this paragraph. And we can see, if you go to this paragraph, you will see two important things in this paragraph. Okay. Firstly, that the table QW 432 define the F number of the different filler metals. Okay, this is very important. This is a new table, very important. Okay, and secondly, this paragraph established that a change from a F number to another F number is considered a change in essential variable. So this means that change the F number used in the test coupon require a new welding qualification or a new PQR. Okay, this concept is important because define the qualified range of these variables. The F number used in the test coupon is the same that shall be included in the WPS. You can change the electrode into the qualified F number. However, you can modify in the WPS the F number used in the test coupon or PQR. Okay, this is the qualifier range in this variable. Okay, so here we have the table QW 432, and this table is divided in 3 columns. The first one, okay, and show us the F number assignment. Okay, the second one define the ESME specification. Okay, this is the specification of the filler metal, very similar to the specification of the base metals. Here I have a image. Okay. Okay, and finally, the third column has the AWS classification into the filler metal specification. Okay, how this table is used? Okay, Okay, so we will work with a specific example. For example, the SFA 5.1 E7018, this electrode. Okay, so here we have the definition of this electrode. When we use this table, we have to begin. With the second column. Okay, this is the column, the third column that we have to use, the second column. And in this column, we have to find the ESME specification of our filler metal. When we have identified the specification, we shall to find the AW's classification, and then we have to define the F number. As easy as that, okay? So here we have our material specification, in this case for the filler metal. So sorry, this is, okay? And then I have to search and find the AW's classification, okay? So here we have very important, something that is very important. So in this case, the F number for this electrode is F number 4, okay? So please check the AW's classification. And this classification only includes the last 2 P numbers because they define the operative characteristic of the filler metals, okay? The first and second number in the WPS and in the WPS classification is replaced by 2X because these 2 numbers indicate the tensile strength in all weld metal, okay? However, in these variables, the values are not relevant due to the fact that the grouping is based on operating characteristics, which are defined by the last number in the AW classification, okay? So this is the last quick exercise. It's very easy, and approved test coupon was welded using an SFA 5.588018 C2, okay, electro. This is a typical electrode from chromium and molybdenum steels, okay, low alloy steels. So you have to define the F number for this electrode, okay. Come back to the table, and okay, I have the table here. So I will go to the ASME. Can you see the first page of the ASME? Go.
Yeah.
Yeah. Okay. Okay. Here we have the table. So in this case, our electrode is SFA 5.5. This is the filler metal specification, and our electrode is this classification, okay, AWS classification. So this electrode is an F number 4, okay. This is the qualified range. You can see that into this group you have a lot of electrodes, okay, that you can replace into the qualified range, okay. So I come back to the presentation. So this is the last presentation, okay. A very simple case study to work together. Here we have a coupon test that was welded with the following variables, okay. We have a seamless pipe according to this material specification. We have a base metal thickness. Here we have the base metal thickness, and this is the electrode, okay. This is our coupon test. These are our actual variables, okay. So the question is, is it possible to use this test coupon to qualify a WPS to the following production welding? Okay, so in this case, we have to define the qualified range of each variables, of each actual variables, and define if possible weld this condition, okay, this product to the production welding, okay. So I will go to I will go into the blackboard. I think that's more easy, fast. So, excuse me. Okay. Our PQR has these actual variables. So, base metal. This is an austenitic stainless steel, okay, seamless pipe. And the thickness, 5 millimeters. And the electrode, SFA, 4.4 E. Okay, so I have to define the qualified range. Okay, in this case, I have to go to table QW 422, and then I have to go to the table QW 424. Here I define the P numbers of this material, and here I define the qualified range. The P number of this material is P number A, okay, and the qualified range are all P number A, okay. So then I have to define the qualified range of base metal thickness. I have to go to the QW 451.1. So, and according to this thickness, define the minimum and maximum qualified. Okay. In this case, this thickness, the range of thickness are from 1.5 millimeters to 10 millimeters. Okay. And finally, I have to define the F number. Okay. I have to go to the table QW 432 and define the F number. In this case, the F number is the F number 5. Okay? So now I have to compare this qualified range, okay, this qualified range with the production welds and decide if possible weld this production weld with this PQR, okay? So, conditions in production welds are a plate with this material specification, okay, and then a thickness between 5 millimeters to 13 millimeters, and then electrode F5. Okay, so I have to define the P number for this material, to compare with this with the actual variables and the qualified variables. So in this case, this material is a P number A. Okay, so we can see that this material is according to this qualifier range. Okay, with this PQR, okay, I can write a WOPS to weld this P number A. So go to the electrode. Okay, in this case, the electrode is an austenitic stainless steel electrode. In this case, it is F number A, not number 5, pardon. So sorry. This electrode is covered by this PQR. Okay? So the problem is in the thickness of the base metal. Okay? This production weld, the thickness is between 5 millimeters and 17 millimeters. And the qualifier range, according to these actual variables, are from 1.5 millimeters to 10 millimeters. Okay? So I have a range out of the qualified range. Okay? So here I have a problem. So this is essential variable. This is an essential variable. So I have to qualify a new welding procedure, okay, to cover these variables. Okay, this is the concept. Okay. This, I think that's okay. Okay, we are okay with the time. Okay, do you have any question? I think that I know that it was very, very fast. So sorry, but it's a lot of information in this time. But do you have my email? Okay.
Hi, Andres. I have a question, if you don't mind. I can kick off. First of all, I just want to say that I've gone to a lot of several ASME 9 courses, and I must say I'm pretty impressed that you were able to condense it all into an hour and 20 minutes. So thank you very much for that.
Okay.
Also, I just want to ask, with the heat input, like heat input is typically supplementary essential variable. It's not really an essential variable, but heat input affects the ductility, right? So I just find that it's kind of odd that it's not typically an essential variable.
Okay, I think that, so sorry, I have to improve my English. Perhaps I have a problem with the interpretation of the question. I think that it's much better for me if you write in the chat.
Sure,
okay?
Sure.
Excuse me. Okay, I have a question about the F number for gas metal arc welding. In the case of arc metal arc welding, all filler metal are included in the F number 6. Okay, in the X number 6, and it's typically that this material are included in the filler metal specification SFA 5.18. Yes, and all AW classification into this filler metal specification are included in the F number 6. Okay. Okay, I want to answer the previous question. I don't know if writing in the chat. Okay. 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 Why the heat input is not essential? Okay. Okay. It's not essential because the heat input is a supplementary essential variable. Okay. Because I know that we can discuss this conclusion. Okay. But the answer is that the heat input to the ESME section 9 is applied to is an supplementary essential variable because it strongly affects the toughness of the materials and is defined by the code construction, the requirement of this supplementary essential variable. The answer your question is that the heat input is not essential because it's supplementary essential variable into according to the definition and the investigation of the ESME section 9.
Well, Andres, this is fantastic. I'm so grateful. I have to say,
okay.
I this myself.
Okay, I promise you improve my English to the next opportunity. Okay.
This is great. So for everybody in the class, Andres just put his email address. If you have questions, let me tell you, he's volunteering to answer your questions. But if you want to ask the same questions to any consultant, it's going to cost you big bucks. So take advantage of this. I think you can. I believe U of A has ASME 9 available online to students.
Okay.
Crazy. That's incredible thing to have. And on that note, in addition to say many thanks to Andres, I will be in touch with you all as you submit your report and your project. And I really hope to see you in person when the university reopens and you come to see our lab and you'll see everything I promise and more.
Okay. Okay.
So,
okay.
Thank you, everybody.
No,
thank you, Andres.
Thank you for everyone. Thank you, Patricio and Alejandro for your help for this opportunity. And it's a pleasure for me. It's a pleasure for me. Thank you very much.
Thank you very much, Andres. Great presentation. Thank you, Dr. Mendez.
Thank you. Thank you.
Thank you, everybody. I hope you enjoyed the class.
That was excellent. Thank you.
And this is the last class. Okay. Congratulations. Congratulations
yes.
for everyone. Okay.
So until soon, everybody, do well in your finals.
Thank you.
I just wanted to say thank you, Dr. Mendez. You were really helpful during this hard time.
Oh my God, thank you so much. That means a lot to me. This class is certainly an act of love, and I hope, I promise you when you have a job, you'll be so happy you took it.
Yeah, thanks again.
Absolutely.
Okay.
Andrés, te voy a llamar por WhatsApp.
Okay, okay, excellent.
Bueno, entonces te saludo de acá, Andrés.
Ale, un gustazo, che, muchas gracias por la ayuda.
La verdad que estuvo bárbaro, ¿eh?
Bueno, fuimos.
Leíste a la velocidad de la introducción de los materiales, ¿te acordás?
¿Qué pasó?
No, es muy difícil porque por ahí tengo ganas de profundizar en algún tema y la limitación del idioma, bueno, pero...
Yo creo que se entendió bárbaro y pudiste dar un montón de cosas en poco tiempo.
Sí, no, Andrés, mucho gusto. Me llamo Eduardo. Eddie. No, hombre, es que lo hiciste muy bien, en muy poco tiempo, impresionante.
Ok, bueno, muchas gracias, muchas gracias.
Sí, sí.
Fue la verdad que muy muy interesante para mí, como primera experiencia. Digo, estos cursos acá en la Argentina, estoy prácticamente todas las semanas, pero bueno, darlo para una carrera universitaria, en otro idioma, con otros objetivos, que sé que usted le mete mucho a cosas muy profundas de la soldadura, la verdad que está bueno. Así que bueno, muchísimas gracias. Ahí está mi contacto, cualquier cosa lo que los pueda ayudar, estoy a disposición.
Okay. Muy bien, gracias. Ahí le mando un email, porque sí tenía unas cuantas preguntas. Pero...
Ok, excelente.
Falta ir a WhatsApp. No, espectacular. Sabes que esta clase la vengo enseñando hace como 10 años, y una de las razones porque traigo un experto es porque no tengo la menor idea de los códigos. Pero por primera vez creo que empiezo a tener... te voy a hacer más preguntas. Creo que empiezo a entender cómo funciona la mecánica. Fue buenísimo, buenísimo.
Me alegro, Patricio, me alegro. Muchas gracias por la oportunidad, en serio.
Sí, mira, muy probablemente el año que viene el Teaching Assistant sea Eddie, así que Eddie anda tomando nota, porque esto...
No, sí. Tomé notas. Me encantó cómo son las flechas y relacionando las tablas, porque es ¿cómo se dice? Como un telarañas.
Telarañas, tal cual. Yo siempre digo que los códigos, pues la gente a veces entra al código y claro, no sabes por dónde empezar. Los códigos realmente no son difíciles de usar. O sea, lo que hay que hacer es aprender la mecánica del código. Y los códigos tienen, por ejemplo, el ASME, cuando entendés por ejemplo, algún código de construcción, yo laburé mucho con los códigos nucleares, y cuando aprendes un código de construcción, te querés pasar a los otros, los de caldera, recipientes a presión convencional, que sea, y estás leyendo prácticamente el mismo código, la misma mecánica siempre. Y en eso son bastante benévolos los códigos. Pero bueno.
Sí. Algo que a mí me interesa bastante es cuando, por qué dicen lo que dicen, ¿no? La plata está en aplicarlo sin preguntar, pero yo quiero preguntar igual.
Sí, no, yo coincido con vos y yo, por ejemplo, te cuento una anécdota, por ejemplo, en uno de los IWG acá en la Argentina vinieron expertos de AME, estaba Esperco, bueno, habían varios pesos pesados de AME. Y me acuerdo que, por ejemplo, hay algunas cosas medio extrañas, que la sección, por ejemplo, la sección 3 de la parte nuclear, en cosas como los socavados, te permite 1 milímetro de profundidad, y la sección 8, que supuestamente es para componentes no nucleares, te permite 0,8 máximo. Y vinimos y le preguntamos, así de curiosidad, y nos dijo, no, lo que pasa es que eso depende de la experiencia en servicio, no es que nadie estudió si hay una cuestión fractomecánica detrás de ese 0,8, que sea 0,8, que sea 1, y encima dice, para colmo no nos hablamos con los de nuclear nosotros. Es como que cada comité tiene sus cosas, pero hay cosas a mí que al que se ha metido un poco en la parte de metalurgia, por ejemplo, que los parámetros de proceso no sean variables esenciales, cosas de ese tipo. Está buena la pregunta que hicieron, ¿por qué el calor aportado no es también una variable esencial?
Sí, esa fue mi pregunta, porque a mí siempre me parece muy raro. Sí, es supplementary, ¿no? Pero por definición, el heat input afecta la ductilidad del material, ¿no?
Sin duda que sí. Hay algunas cuestiones que los códigos definen simplemente, como te digo, por experiencia en servicio o por prueba y error, y esos criterios que yo lo decía al principio, están muy basados en experiencia en servicio, los meten en los códigos como verdad irrefutable, y por ahí vos empezás a buscar y no encontrás el fundamento, porque realmente quizás no lo haya. No es que haya un trabajo enorme de investigación en donde hayan visto que el calor aportado afecta, porque todos sabemos que sí, ¿no? Está más basado en otras cosas. Pero bueno, es muy interesante en ese sentido.
Muy bien.
Andrés, gracias eternas. Te estoy mucho en deuda.
No, por favor, al contrario.
Después que nos explicaste ASME9, que es la razón de la vida, te puedo explicar el plasma, el cathode fuel, el electrodo cuando quieras.
No, excelente. No, el año que viene te voy a invitar a las clases de acá del sábado para que nos puedas desburrar, como decimos acá, respecto a la física de la arte.
Mira, yo creo que mientras hablemos, vamos a tener lo mejor de cada uno. Y si no hablamos, tenemos lo que tenemos. Y esto es bueno.
Ok, bárbaro, buenísimo. Bueno,
¿estamos? Sí.
¿Cómo?
Estabas diciendo algo, perdón.
No, nada.
Entonces, mira, la vamos a seguir por email. Ahora una chica de India quiere hablar, que para ella creo que son las 3:30 de la mañana, así que no la quiero dejar esperando mucho más.
Ok.
Esto es fantástico y después seguimos hablando también con los otros proyectos ahí en Argentina y las otras cosas.
Dale. Excelente. Bueno, muchísimas gracias de vuelta. ¿No? Cualquier cosa estamos en contacto.
Será hasta luego, ¿eh? Qué bueno que Eddie, después me vas a dar los comentarios para empezar a prepararnos hacia el año que viene.
Sí, claro. Bueno, mucho gusto, Andrés. Gracias.
No, por favor.
Gracias, doctor.
Voy a cortar. Chau.
Hasta luego, bye.